The longest common subsequence problem, where computers get to play spot the difference at a level of complexity that makes human proofreading look like child's play. The LCS problem, because finding common ground is hard. So what exactly is the LCS problem? Well, it's a classic problem in computer science and bioinformatics. It involves finding the longest subsequence common to two sequences. Sounds simple, right? But trust me, it's more challenging than it appears. The LCS problem is all about finding the longest sequence that appears in order within two given sequences, but not necessarily contiguously. Think of it as matching puzzle pieces that don't have to be next to each other. For example, if we have sequence 1 as A, B, C, D, E and sequence 2 as A, C, E, the LCS would be ACE. LCS has real-world uses, from text comparison to DNA sequence alignment, where spotting common patterns efficiently is crucial. Now let's dive into the recursive approach. It's one way to tackle the longest common subsequence problem, though not the most efficient. A basic, red terrible approach to LCS is recursion. First, compare the last characters of both sequences. If they match, add that character to the LCS and continue. If they don't, ignore one character from either sequence and try again. This works, but at a horrific computational cost, an exponential nightmare as sequences grow. Essentially, it's like searching for a book's most important sentence by reading every possible combination of words in every possible order. Not ideal. The classic struggle. Here we see a programmer watching their recursive LCS function slow to a crawl. But don't worry, there's a better way. Dynamic programming optimization to the rescue. Thankfully, dynamic programming comes to the rescue, eliminating redundant calculations. Instead of recomputing solutions for overlapping subproblems, we use a table-based approach. A two-dimensional table stores LCS lengths for every possible portion of the sequences. We build solutions incrementally, calculating each step only once. The result? A solution in O of m times and time, a massive upgrade from recursion. Imagine a grid filling up, solving the longest common subsequence in a structured way. Meanwhile, recursion spirals into madness, showing the stark contrast between the two approaches. So where does the longest common subsequence algorithm find its place in the real world? Let's explore its diverse applications. The longest common subsequence isn't just an abstract algorithmic curiosity. It powers text comparison and version control, used in Git and diff utilities to track changes between document versions. In bioinformatics and genetics, it is essential for DNA sequence alignment, revealing genetic similarities. For data compression, it helps detect repetitive patterns for more efficient storage. In natural language processing, it assists machine translation by aligning similar sentence structures. And lastly, in multimedia editing, it finds similar segments in video and audio, streamlining editing workflows. Visual examples can really help bring concepts to life. Imagine Git highlighting changes in a file, DNA sequences aligning perfectly, and an editor seamlessly matching video clips. These are just a few ways we see these principles in action. And there you have it, folks. We've journeyed through some fascinating aspects of dynamic programming and its real-world applications. The longest common subsequence problem showcases dynamic programming at its finest. Instead of an exponential recursive disaster, we get a structured, efficient solution. Next, we'll dive into another dynamic programming marvel because, let's face it, making computers think efficiently is what we're all here for. I am your guide, Antonio Klim. May the pseudo powers be always with you.